Okay, so now we are going to start a new chapter. Okay, so which is going to cover all the power cycles. Okay, so first of all we need to know what is power engineering. Okay, power engineering nothing but it is the engineering or the subject which helps us to find the ways of how to get work output. Okay, or how to produce continuous work using or giving another form of energy. Okay, so power engineering is generally divided into three parts: steam power plant, power plant, and IC engine. That means in real world, whatever the power is going to get generated, okay, with the help of other alternative energy, that are steam power plant. Okay, steam power plant means whatever the working fluid that has been used inside the parts, okay, inside the parts of an engine, okay, is going to be water or steam. Okay, that means phase change is going to take place inside the steam power plant. Next is power plant. Okay, gas power plant, in these machines we are going to use the gas. Okay, and the third one is IC engine. IC engine is also, you can say it is gas, but the air which we take, it burns inside the engine only. Okay, so these are known as internal combustion engine. Okay, so these are of two types: Otto cycle and diesel cycle. Gas power plant is generally, you can say, Breton cycle. Okay, in Breton cycle we use gas. Okay, and in steam power plant is generally Rankine cycle. Okay, so we are going to see it here also. So power cycle is what? This is a cycle in thermodynamics which is going to give us work with the expense of heat. Okay, with the expense of heat. Now this power cycle is divided into two other parts: steam power cycle and gas power cycle. In steam power cycle, what happens? The working fluid changes phase. As I have told you earlier, that the working fluid is going to change its phase throughout the process, or throughout the cycle it is going to change its state. Okay, change its state means whether liquid is becoming gaseous, and gaseous is again becoming liquid. Okay, so and example of this vapor power cycle is going to be your Rankine cycle. In gas power cycle, what happens? The working fluid is always gas inside the parts, okay, machine parts which you are going to use. Okay, that means whatever the working fluid you are going to use throughout the cycle, okay, throughout the different parts of the cycle, like compressor, turbine, and then evaporator, etc. Every through every part, whatever the working fluid is moving, okay, these will be continuously gaseous. Okay, like this, it is not going to change the phase. Okay, so example of such type of this is Breton cycle, Otto cycle, and diesel cycle. Here the example is for vapor cycle, it is Rankine cycle. Okay, so now we are going to start with our Breton cycle. Okay, okay, so now we are going to see the assumptions. Okay, for air standard cycle. Okay, assumptions for air standard cycle is air is going to be the working fluid which is treated as an ideal gas. Okay, the working fluid whichever it is in the machine parts, okay, different machine parts for completing the cycle. Okay, that working fluid is going to be our air, and it will be considered as ideal gas. Cp and Cv are constant, so obviously if ideal gas is there, the Cp and Cv value are going to be constant. Okay, closed system is considered which undergoes a cycle. Okay, so whatever the cycle we are going to consider, okay, in that cycle there is no mass transfer. Okay, there is no mass transfer is going to be assumed. Okay, so that means that complete cycle is going to be inside a closed system. Okay, combustion process is replaced by equivalent amount of heat addition from external source. Okay, so in processes or in cycles like Otto engine or diesel engine, okay, what happens? The combustion of the fuel takes place inside the cylinder. Okay, now this combustion of the fuel is replaced. Okay, the combustion of the fuel is replaced with external heat addition process. Okay, or heat addition process from some external source. Similarly, exhaust process. Okay, when the burned or combustion products are there, it is going to exhaust. Okay, then this process is going to be get replaced with the equivalent amount of heat rejection. Okay, so this is going to, the combustion products is going to have some heat quantity. Okay, so after when this exhaust is going to take place, okay, then we are going to replace that exhaust process with the equivalent amount of heat rejection from the system. Okay, okay, so now we are going to read gas power plant. Okay, gas power plant is generally based on Brayton cycle. Okay, and that Brayton cycle is also known as Joule cycle or constant pressure cycle. Okay, so before starting, we must know that for understanding Brayton cycle, simple Brayton cycle are of two types. Okay, open Brayton cycle and closed Brayton cycle. Okay, in closed Brayton cycle, what happens? The same air is going to recycle inside the cycle, and in open Brayton cycle, it takes in some air from atmosphere, whatever the process it needs to be done is been done, and after that whatever the burned air is there, it is released into the atmosphere again. Okay, so this is known as open Brayton cycle and this is known as closed Brayton cycle. So first of all we are going to understand what is open Brayton cycle. Okay, okay, so now this is our open Brayton cycle. Okay, in this cycle what is there? One compressor is there, one turbine is there, and one combustion chamber is there. Okay, so open Brayton cycle takes in some air from atmosphere. Okay, it takes air from atmosphere. Okay, after that what happens? It compresses. The compressor compresses the air adiabatically. Okay, so after compressing, its volume is now decreasing. Okay, so this compressed volume, its volume is also decreasing, its pressure has increased and temperature is also increased due to the compression, forceful compression of the air. Okay, now as the high temperature, high pressure is now inserted into the combustion chamber. After combustion chamber, what is happening? Some fuel injection is going to be there, and the air fuel mixture is now going to burn. Okay, the air fuel mixture or the combustion process is going to get completed in the combustion chamber. Okay, now after combustion, it is again having the high temperature and high pressure. Okay, this high temperature and high pressure air is now again going to expand in the turbine. Okay, and while expanding, the turbine is going to do some work. Okay, that means the turbine helps us to the air. Okay, the high temperature, high pressure air which is going to get expanded into the turbine. Okay, and that expansion process is going to give us some work. Okay, so in this way we are getting work, and after expanding, this is going to be the exhaust. Okay, or the combustion products are going to go out into the atmosphere again. Okay, now if you want to see the PV diagram, okay, PV diagram, what happens? First, up to some volume 1, it is going to insert some air. Okay, or it is going to take in some air into the compressor. Okay, so after taking it to the volume 1, it is going to compress adiabatically up to volume 2. Okay, that means up to point 2 it is going to get compressed. Okay, and that is going to be adiabatically. After that, what happens? Keeping the pressure constant. Okay, in constant pressure, it is going the heat addition is going to be there. Okay, so this process is going to be in constant pressure. Okay, and this process is nothing but our heat addition process, Q in. Okay, and this is our Q out. Okay, or Q rejected. Okay, so in the assumptions we have already said that whatever the combustion process is there, okay, whatever combustion process we are going to see is going to be get replaced with the equivalent heat addition from external source. Okay, that combustion process is completely going to get replaced with heat addition from external source. Okay, so after that, what is happening? It is again expanding adiabatically in turbine. Okay, so adiabatically it is going to expand in turbine, and it is going, after expanding, the volume is going to be at 4. Okay, now if you get confused by the fact that you are going to take in this much volume of air. Okay, so during the exhaust, this has become this much amount of air. Okay, so after inserting, there is a heat addition process. Okay, and some fuel injection is also there. So whatever we are getting at point 4 is nothing but the combustion products. Okay, combustion products. So volume may change due to the heat addition process. Volume may get changed, but whatever the mass was inside the system is not going to get changed. Okay, volume can change. So after 4, it is going to leave the combustion products into the atmosphere. Okay, or it is going to deposit the combustion products into the atmosphere. So from point 4 to 1, okay, the process is unknown. From process 4 to 1, but we know that 4 to 1 is exhaust process, because the next cycle is again going to start from point 1. Next cycle is again going to start from point 1. So there must be a path through which we can come to point 1 from point 4. Okay, Now we have said that this is the exhaust process, okay, and you have in assumptions we have also said that whatever the expansion exhaust process is there, that exhaust process is going to get replaced with equivalent heat rejection from the system. Okay, so this is the heat rejection process from the system. Same thing if you draw it on TS diagram. Same thing if you draw it on TS diagram. The first process is what? Adiabatic. Okay, reversible adiabatic. First process is reversible adiabatic. Now we have already seen that reversible adiabatic process is always isentropic. Okay, so in temperature entropy diagram from 1 to 2 the process is going to be adiabatic, and we have also seen that it is constant pressure, and we have also seen that the constant pressure line goes like this in TS diagram or temperature entropy diagram. The constant pressure process goes like this. Okay, and the temperature is also getting increased from 2 to 3. The temperature is also going to get increased, and this is the constant pressure line. Okay, now from 3 to 4 is again what? Adiabatic expansion. So adiabatic means isentropic, reversible adiabatic means isentropic. So isentropically it is coming down to 4 1. Again the path is not known, but we are assuming that it is going to be constant pressure. Okay, we are not sure, so that's why we are replacing it by dotted lines. Okay, now the next cycle is again going to start from point 1. Okay, so from the previously discussed part we have said that we do not know the path. Okay, but one thing is definitely sure, that the point 4 and point 1 is going to have same pressure. Okay, how? Because when point 1 is reached, okay, that means it is taking in the atmospheric air. Okay, the atmospheric air initially is going to have the pressure of atmosphere only. Okay, now while expanding and leaving it to the atmosphere is also going to have the pressure of atmosphere only. Now point 4 and point 1 is going to have the same pressure, but the path we don't know. So if these two are going to have same pressure, that is the reason we are going to take this pressure parallel to the volume axis, so that it means it is constant pressure. Okay, otherwise point 4 and point 1 are going to have the same pressure. Okay, now from these processes there are something we need to know. So Rp, small r suffix p, is going to be our pressure ratio. Okay, pressure ratio is what? Pressure ratio is nothing but the ratio of higher pressure to lower pressure. Okay, so here higher pressure is P2 and lower pressure is P1. Okay, again in that side P3 and P2 are same. P3 and P2 are going to be same because it is constant pressure process. Okay, so P3 and P2 are same. P4 and P1 are also same. So P2 by P1 becomes P3 by P4. Okay, now from the equations, all the equations in the specific heat you will get to know. Okay, so what is the equation for adiabatic process? Okay, for adiabatic process there is a relation like this: T2 by T1 equals to P2 by P1 to the power gamma minus 1. Okay, if you check the notes you are going to find this relation. Okay, now again P2 by P1 is what? P2 by P1 is nothing but the pressure ratio. So we are writing T2 by T1 is equals to pressure ratio to the power gamma minus 1 divided by gamma. Okay, similarly for process 3 to 4, it is also adiabatic. So similar relation is going to come. So T3 by T4 becomes P3 by P4 to the power gamma minus 1. Okay, gamma minus 1 by gamma. So T3 by T4 again becomes P3 by P4 is again what? Pressure ratio. So pressure ratio to the power gamma minus 1 by gamma. Now this is also a pressure ratio, this is also a pressure ratio, but the left hand side are not same. Okay, so since these right hand side are going to be same, so obviously left hand sides are going to be equal. So we have written T2 by T1 equals to T3 by T4. Okay, so from this relation we can write T4 by T1 is going to be equal to T3 by T2. Okay, now coming to the efficiency of the open Brayton cycle. What is going to be there? Now you know efficiency is what? W net work output divided by whatever the energy input we are going to give. Okay, so this is QE. Now we are replacing W net by Q in minus Q1, because we know that for a cycle, the first law of thermodynamics for a cycle tells us that the net work interaction is going to be equal to net heat interaction. So we are replacing net work interaction with net heat interaction. Okay, now if you simplify this you are going to get 1 minus QR by QE. Now what is Q rejected? Q rejected is this one. This is a constant pressure process we are assuming. Okay, so for constant pressure process we know that it is going to be m into Cp into temperature difference, mass into specific heat at constant pressure into temperature difference is what is the temperature at T4 minus what is the temperature at T1. Okay, so T4 minus T1, and what is Q in is this constant pressure process. Q in is there, so this is going to be the mass of air which it is taken in. Okay, mass into specific heat at constant pressure into temperature difference during this process is what? T3 minus T2. Okay, so mass and Cp are going to get cancelled out. Now remaining thing is T4 minus T1 and T3 minus T2. Now what we are doing, from the numerator we are taking T1 as common. Okay, after taking T1 common, what is remaining? T4 by T1 minus 1. T4 by T1 minus 1. And from the denominator we are taking T2 common. Okay, T2 are going to take common, and then what is going to be that? T3 by T2 minus 1. If you take T2 common, it is going to be T3 by T2 minus 1. So here we have found out that T4 by T1 is going to be equal to T3 by T2. T4 by T1 is going to be equal to T3 by T2. So these two are going to get cancelled out, and the remaining thing is 1 minus T1 by T2. Okay. Okay, so this was the expression of efficiency what we have got. Okay, now if you remember, we have found out that T2 by T1 was Rp to the power gamma minus 1 by gamma. Okay, now the equation has come T1 by T2. Okay, and this equation is T2 by T1. Okay, so that means the reciprocal of this will replace this one. Okay, if we replace this by Rp, then the reciprocal of this is going to come. So this is going to be 1 minus 1 by Rp to the power gamma minus 1 by gamma. Okay, now if the temperature is given, then also you can find the efficiency, and if the pressure ratio, only the higher pressure and lower pressure is given, then also you can find out the efficiency of the Brayton cycle, okay, or open Brayton cycle. Now this is the way this is going to vary. Now if you see, if Rp is going to increase, means what? This value is going to get decreased. If this value is going to get decreased, then this whole value is going to get increased. Okay, that means if Rp is increasing, then efficiency will also increase. Okay, now if the gamma value is going to increase, so if gamma value is going to increase, so here we have written that gamma 2 is greater than gamma 1. Okay, gamma 2 is greater than gamma 1. So when the gamma is more, with the increase of pressure ratio, the increasing efficiency will also be more. Okay, that means for the same pressure ratio, gamma 2 is going to have the higher efficiency than gamma 1. That means what? When the adiabatic index is going to be more, okay, with the increase in pressure ratio, the efficiency will be increasing more in case of higher adiabatic index. Okay. Okay, so there are some limitations of the open Brayton cycle. Okay, the first limitation is working fluid is air. As now we have said that with the increase of the adiabatic index, the increase in efficiency would be more for the same increase of pressure ratio. Okay, now in open Brayton cycle we are going to take atmospheric air. Okay, that means we are going to take air only. So the gamma is limited. So even if we try, we cannot change the adiabatic index. Okay, so if we want to increase the adiabatic index for the same pressure ratio, it is not going to happen, because the working fluid used is always going to be air, and its gamma is limited. Second thing is that it is going to use only high quality fuels. Because of what? Because the burned, okay, or the combustion products of the air fuel mixture is directly going into the turbine. If it is directly going into the turbine, that means what? Directly it may corrode, okay, or erosion may take place into the turbine. Okay, so only the high quality fuels are going to be used. And another thing is that open Brayton cycle, the whole system is going to be lightweight. Okay, the weight of that whole open Brayton system, or whatever the parts are there, is going to be very lightweight. So this type of system is going to be well suited for aircraft. Okay. Okay, so now we are going to see closed Brayton cycle. Okay, previously we had seen open Brayton cycle. In open Brayton cycle, there are interaction with the atmosphere. Okay, now there is no interaction with the atmosphere. Whatever medium we are going to give, this will only rotate about the whole parts, okay, of this cycle, okay, and will continue the cycle. Okay, that means if you are going, suppose inside it we are giving some air. Okay, so it will first, from 1 to 2, it is going to compress the air. Okay, it is going to compress the air. Next, what is going to be there? We are going to give some heat input. Okay, so previously in open cycle what we had done, we had given some fuel injection. Okay, that means what, the combustion, okay, the combustion of air fuel mixture was there. Okay, and through the turbine the products of the combustion of that air fuel mixture were passing through the turbine. Okay, so initially the heat addition was by fuel injection. Now what we are going to do, we are going to shift the combustion chamber out of the cycle. Okay, if the combustion chamber will be somewhere else, only the heat, okay, only the heat produced from the combustion chamber is going to heat with the help of a heat exchanger. Here this one is one heat exchanger. Okay, with the help of that heat exchanger, what will happen, whatever air that has been compressed up to point 2, okay, will pass through this heat exchanger, and in this heat exchanger we are going to give heat which we have received from the burning of the fuel from the combustion chamber. Okay, that means previously whatever air were passing through the compressor, and the compressed gas was burned. Okay, or the combustion of that gas coming out from the compressor used to take place. Okay, with the help of some fuel injection. Now what we are going, we are now taking only the heat. Okay, from the combustion chamber we are taking only the heat, and we are not burning the air. Okay, we are just heating the air. Okay, the compressed air is heated in the heat exchanger. Okay, and it is allowed to pass through the turbine. Okay, now in this case what we have done, the by compressing the air we are going to increase the temperature and pressure of the air. Okay, which is acting as the working fluid. Okay, for this cycle whatever is going to be acting as the working fluid, that fluid is nothing but compressed. Okay, so with the compression what is going to be there, the pressure and temperature is going to increase. Now by passing it through the heat exchanger, that means by heating it. Okay, so this is the process of heat addition. This is the process of heat addition. By heat addition what we are doing, we are again raising the temperature of that compressed air. Okay, we are again raising the temperature of that compressed air. Now the high temperature and high pressure gas is now allowed to expand in this turbine. Okay, through this turbine. Okay, so this during the expansion through the turbine there is going to be some shaft work. Okay, there is going to be some shaft work. Okay, after that what happens, now in open cycle what we had done, we had released, okay, released whatever the product used to expand through the turbine, we had to release it to the atmosphere. Okay, now we are not releasing it. Okay, that means the expanded gas, okay, after expansion the gas is having somewhat temperature. Okay, so this is again allowed to pass through another heat exchanger. Okay, so now what we have done, previously we had given some heat input. Okay, now while passing through this heat exchanger, what is going to be there, we are passing some cold water. Okay, and in return some hot water we are going to get. That means what, whatever the gas was coming through this line, okay, is getting cold. Okay, is getting cold with the help of this cold water. That means in this process what is happening, some heat rejection is going to be there. Okay, because whatever the gas is coming, okay, through this passing through this heat exchanger is going to lose the heat to the running cold water. Okay, that means now whatever the gas was coming through this heat exchanger is going to have a low temperature. Okay, and again this is going through the compressor, okay, which is going to get compressed and heated in the combustion chamber or the heat exchanger after the turbine. In this way the cycle runs on. Okay, in this way a cycle is running on. Okay, so this is the concept of our closed Brayton cycle. Now in the next board we are going to represent this closed Brayton cycle in PV diagram and temperature entropy diagram. Okay, okay, now this is going to be our PV diagram and this is going to be our PS diagram. Okay, so 1 to 2 is what, 1 to 2 was compression. Okay, or there was a compressor. Okay, the compression takes place adiabatically. So 1 to 2 is going to be our adiabatic compression. 2 to 3 is going to be our heat addition. Okay, but the heat addition takes place in a constant pressure process. Okay, so if you remember, we have said that Brayton cycle is also known as Joule cycle or constant pressure cycle because it has two processes which are at constant pressure. Okay, so heat addition process is constant pressure process. Okay, from 2 to 3. Again, if you remember, from 3 to 4 it was turbine. Okay, turbine means there is going to be some expansion. 3 to 4 is nothing but adiabatic expansion. Okay, so after reaching at point 4, it is going to pass through another heat exchanger where the working fluid is going to lose some heat. Okay, and that heat is nothing but Q rejected. Okay, that is Q1. Similarly, if you plot this on PS diagram, if you plot this in PS diagram, 1 to 2 is what? 1 to 2 is adiabatic process. Okay, now reversible adiabatic process is always isentropic. Okay, now due to compression, temperature always increases. Okay, that's why it is going from 1 to 2. Otherwise it would have gone from 1 to 2. Okay, in the downside. But since due to compression the temperature increases, that's why 1 to 2 is going upwards. Okay, so it is isentropic process, or reversible adiabatic process is going to be isentropic process in TS diagram. Okay, so this this is constant pressure line in TS diagram, and this is also constant pressure line in TS diagram. Okay, so second thing, 2 to 3 is going to be what? Heat addition process but at constant pressure. Okay, in TS diagram constant pressure line is like this. 3 to 4 is again what? Adiabatic process. So here it is going to be isentropic process. 4 to 1 is again constant pressure heat rejection process. So 4 to 1 is again in TS diagram at constant pressure heat rejection. Okay. Okay. So efficiency of Brayton cycle is going to be same as that of efficiency of open Brayton cycle. Okay. So the Brayton cycle was 1 minus T1 by T2, exactly same. Okay. But the only difference is what? We did not know the path. Okay, we did not know the path in open cycle. Okay, but in this cycle, in this closed Brayton cycle, we know what is the path, and we know that the pressure is going to. In the previous one also, we had known that the pressure at point 1 and pressure at point P was same. Okay, only we did not know the path. Okay, so the everything is going to be same, even the efficiency is going to be same. Okay, now from the relation we have found out that T2 is equal to pressure ratio to the power gamma minus 1 by gamma. So we are going to replace Rp to the power gamma minus 1 by gamma. Okay, now if you see for any cycle, for any machinery, the higher temperature, okay, the maximum temperature is always going to be given to us. Okay, because there is some temperature up to which the parts like compressor or turbine is going to limit themselves. Okay, to avoid any deformation. Okay, that means there is a certain level of temperature up to which the turbine or the compressor or any other parts related in this cycle or involved in this cycle is going to have some resisting temperature. Okay, that means up to some temperature they are going to resist themselves from melting. Okay, now with the factor of safety given. Okay, if there is some factor of safety mentioned, that means after giving some factor of safety, there will be some rated maximum temperature. Okay, that means by anyhow we cannot go beyond that temperature. So we must always remember that if we want to find the or set up any of the Brayton cycle, okay, we must fix the higher temperature or maximum temperature. Okay, by keeping this you can go with a cycle like this also. Okay, this can also be a cycle. You can name this 1 dash, 2 dash, 3 dash, 4 dash. Okay, but we must remember that the highest temperature must be fixed. Okay, so keep remembering this, we are going to design our Brayton cycle or pressure ratio of what we are going to take. So that means in this place for the blue cycle the pressure ratio is going to be smaller. Okay, for the black cycle the pressure ratio is going to be high. Okay, and it is completely depending upon the pressure ratio. Okay, so keeping in mind what is the pressure ratio. Okay, that means if we increase pressure ratio, the efficiency is going to increase. Likewise, we have drawn a graph. Okay, in that graph we had shown that how with the increase of pressure ratio the efficiency used to increase. So for designing this, okay, or for maintaining a efficiency, for increasing the efficiency, we need to increase the pressure ratio. Okay, now pressure ratio we can increase. Okay, but we need to keep in mind that the maximum temperature is fixed. Okay, keeping the maximum temperature fixed, we can increase or decrease the pressure ratio. Okay, and by this we can design a Brayton cycle. Okay. Okay, so now we are going to see what are the advantages of closed Brayton cycle. Okay, the first advantage is low quality fuel can be used. Okay, previously we had said it in disadvantage. Okay, Now we are taking it in advantage. Why? Because previously the combustion of fuel and air was inside the part, okay, and that combustion particles used to go to the turbine. Okay, now our combustion is going to be outside the system, okay, and only the heat is going to be exchanged in the system. Okay, so that is why, as the fuel is going to burn outside the cycle, that's burned or combustion products are not going to come into the turbine or any other parts of the system. So that is the reason low quality fuel can be used. It is not going to hamper the compressor or turbine or whatever the machine parts are used. Second thing is, any working fluid can be used higher value. Previously, since we had taken the air from the atmosphere, that's why we had no other option other than air. Okay, and gamma value was same. Okay, gamma value was constant for that machine. Okay, or gamma value was constant for the working fluid which was moving. Okay, now we can get, or we can use the working fluid according to our wish. Okay, and we can fix, or we can manipulate the gamma value, okay, by changing the working fluid which is going to be running inside the system. Okay, as we have said, if you remember the diagram, we have said that pressure ratio is going to, if pressure ratio is going to increase, the efficiency is also going to increase, and this is the efficiency with higher gamma value or higher adiabatic index. Okay, and this is that means gamma 2 is greater than gamma 1. Okay, that means for the same increase of pressure ratio, the air having, or the working fluid having higher gamma is going to give higher efficiency, okay, compared to the lower one. Okay, so now to increase the efficiency, we can change the working fluid, okay, and we can manipulate the gamma value. We will take a fluid with higher gamma value, okay, and the efficiency is going to increase for that. Third one is clean working fluid is used. Okay, since clean working fluid is used, what is going to be there? The corrosion or the erosion which is going to, the wear and tear which used to happen in case of open Brayton cycle is not going to happen now, because the working fluid which is moving through the machine parts is going to be clean now. Okay, only the clean working fluid is used. That is the reason the machine parts which we are going to use are not going to get the wear and tear very easily, okay, or the chances of getting them are less. And disadvantage, there is only one disadvantage, and in that open Brayton cycle, there was this thing was disadvantage there. Okay, we had said that this disadvantage of this was advantage there. Okay, we had said that due to the open system, as it is taking the air from the atmosphere and it is leaving it in atmosphere, the system is not going to have much weight. Now we are adding two more heat exchangers. Okay, now one is heat exchanger, that is extra, and another thing is the water, okay, cooling water system. Okay, that means two heat exchanger are there. The cooling water system is for cooling down the air, and the heat exchanger was for heating the air. Now heat exchanger is going to rise the weight of the system. So the advantage which was there in open system is now going to become a disadvantage. Okay, so while any of the engine is acting between two temperature limits, okay, any of the engine acting between two temperatures, suppose this Brayton cycle is acting between T3 and T1, there are two temperature limits. Okay, so any engine or any cycle acting between two temperature limits, whose efficiency, and their efficiency is never going to be higher than that of the efficiency of Carnot engine. Okay, that means whatever engines or whatever cycles are there, if they are acting between two limiting temperatures, okay, then none of the engine's efficiency, okay, or none of the efficiency of those engines acting between two temperature limits is never going to be higher than that of the Carnot cycle efficiency. Okay, that we have derived earlier. Okay, so that means Carnot cycle efficiency is going to be the between two given temperature limits. Okay, between two given temperature limits, Carnot cycle efficiency is going to be higher. Okay, always higher. That is going to be the limiting efficiency. Okay, so any of the engine will have efficiency values less than Carnot cycle, or maximum if it can get, it can be equal to Carnot cycle. Okay, it can never go beyond the Carnot cycle efficiency, provided that the temperature limit is given. Okay, here the temperature limit T3 and T4. Okay, if here it is given T3 is nothing but 300 Kelvin and T1 equals to T4 equals to 100 Kelvin. Okay, then there you should remember that here T3 must be 300 Kelvin and here T1 must be 100 Kelvin. In such conditions, okay, that means two temperature limits are going to have the same value. Okay, if such condition is there, that means if between two given temperature limits, if any of the engine is acting, that engine's efficiency is never going to be more than that of Carnot cycle efficiency. Okay, Carnot cycle efficiency is the limiting efficiency. Even for Brayton cycle also it is the limiting efficiency. Okay, so to find out the maximum efficiency, given by the Brayton cycle, okay, up to what extent the efficiency of Brayton cycle can go, the maximum level it can go is the Carnot cycle efficiency. Okay, that is the reason here we have equate these two. Okay, that means Carnot cycle, let us for a moment consider that Carnot cycle efficiency is going to be equal to Brayton cycle efficiency. Okay, that means for highest efficiency of Brayton cycle we are considering this. Now we know that Brayton cycle efficiency is what? 1 minus 1 by Rp. Rp max must be there. Okay, because if Rp is maximum, then efficiency is going to have the maximum value. Okay, if Rp is pressure ratio, okay, depends upon pressure ratio. Okay, if the pressure ratio increases, efficiency of Brayton cycle increases. So for maximum efficiency of Brayton cycle we are writing Rp max. Okay, or pressure ratio maximum pressure ratio. Okay, and the Carnot cycle is 1 minus T min by T max. This is going to be T max and this is going to be T min. Okay, so this is the condition of Carnot cycle and this is the condition of Brayton cycle. Now if you simplify this, you are going to find the value of Rp max. Okay, maximum pressure ratio is nothing but T max by T min to the power gamma by gamma minus 1. Okay, now consider Brayton cycle for a moment. And in the process 1 to 2, okay, for process 1 to 2, this is an adiabatic process, okay, or isentropic process, okay, reversible adiabatic process. So for adiabatic process we know the relation that T2 by T1 is going to be equal to P2 by P1 to the power gamma minus 1 by gamma. Okay, now from here P2 by P1 is nothing but pressure ratio. Okay, T2 is equal to T1 into pressure ratio to the power gamma minus 1 by gamma. Okay, so from here, now in this thing T1 is what? T1 is the minimum temperature. T1 is the minimum temperature. So we are replacing T1 by T min. T2 equals to T min into Rp to the power gamma minus 1 by gamma. Okay. Now after that, if you find the value of Rp from here, you are going to get the value of T2 by T min to the power gamma by gamma minus 1. Okay. Now for this to be maximum, okay, for this to be maximum, here the pressure ratio should be maximum. Okay, so that means this pressure ratio maximum and this pressure ratio maximum are going to be equal. Okay, now if you equate these two equations, okay, here this is also a pressure ratio, this is also pressure ratio. Now if you equate these two, you are going to get this. Okay, so from this you are going to find that T2 is going to be T max. That means what? For max, if you want to find the maximum efficiency of Brayton cycle, you are going to get that T2 is going to be maximum. That means your temperature at point 2 is going to have the maximum temperature if you want to find out the maximum efficiency. Okay, so that means what? Initially it was at point 3. Now if you T2 becomes maximum temperature, okay, T2 becomes maximum temperature and constant pressure line goes like this, and the heat addition process also in constant pressure. So if you T2 becomes maximum, okay, you cannot go beyond this level, this boundary. This is your maximum temperature according to your maximum efficiency condition. T2 is your maximum. So if once you reach the point 2, you cannot go a constant pressure process. Okay, if you go to a constant pressure process, the temperature is going to increase. So you have to stop there only. That means there is no heat addition process. Okay, and then you have to come back from here only. Okay, that means your cycle will go from 1 to 2 and again it will come back to point 1. Okay, if this condition has to happen. Okay, so this will be your 2 dash, this will be your 1 dash. Okay, so this is going to be, your cycle is going to be nothing but a straight line. your cycle is going to be nothing but a straight line. That means what? If straight line is there, if your cycle is only a straight line, what is the area bounded by this straight line? 0. Okay, that means if we try to find out the conditions according to the maximum Breton efficiency, we are going to find out that the W net which we are going to get is going to be 0. Okay, W net becomes equal to 0. Okay, that means if you want to take the Breton cycle efficiency for maximum condition, if you take maximum pressure ratio, then whatever the area you are getting, okay, or W net you are going to get is going to become 0. Similarly, if you want to find out RP mean, pressure ratio minimum, what is the minimum pressure ratio you can go up to? Minimum pressure ratio is what? Is going to be 1, because the higher pressure must be equal to 1. Okay, it cannot come down below this. Okay, so minimum, where can the pressure to come? It can come up to this only. Okay, so if you go for minimum pressure ratio, then what will happen? Then your cycle will go like this, and again it will come back like this. Okay, again it will come back like this. Okay, that means if you want to go for RP maximum, then your W net becomes 0. If you want to go for RP mean, okay, that means minimum pressure ratio. This pressure ratio is just P2 by P1. Okay, what is going to be the minimum pressure ratio? P2 can hardly come up to 1. Okay, for minimum case is what? P2 and 1 will be in same point. So if 1 and 2 are in same point, that means your cycle will go like this and will come back like this. Here also area bounded by this line is going to be 0. And if you put RP mean in this equation, okay, RP mean is going to be what? 1. RP mean is going to be what? 1. If you put 1 here, what is going to be the result? The Breton cycle result is going to be equal to 0. Okay, that means what? If you want to find out the maximum conditions, okay, maximum efficiency conditions, you are not going to get any profit, because if you approach in both the ways, if you go for RP maximum or if you go for RP minimum, the final results you are going to get is 0. Okay, W net becomes 0 for both the cases. So that is the reason why we don't approach for the conditions of maximum efficiency. Rather we go for the conditions of maximum net work which we are going to get. Okay, so for finding out the optimum conditions, okay, optimum conditions, we are going to consider what is the maximum net work we are going to get. If you want to go for the optimum efficiency, then only thing is the disappointment you are going to get, because for all these cases of maximum or optimum conditions with respect to the maximum Breton efficiency, in both the cases you are going to get W net is 0. Okay, so for optimum conditions we do not consider the Breton cycle efficiency anywhere. Okay, so to get the optimum conditions, how my design can be better, okay, for this designing we are always going to consider what is the maximum net work output we are going to get. So in the next board we are going to find out the conditions according to the maximum net work which we are going to get. Okay, so as we have told earlier, to find out the optimum conditions, okay, to find out the optimum conditions in a Breton cycle, okay, we are not going to give importance to the Breton cycle efficiency. Okay, this we have explained it in last board. Okay, we are not going to give importance to the Breton cycle. Rather, we are going to give importance to the net work which we are going to get from a Breton cycle. Okay, so first of all, what we are going to do, we are going to find the expression for the W net, and after that we are going to differentiate this expression with whatever option we are going to have. Okay, so first of all, let us find out what is going to be the W net expression. W net expression is what? Work done by the turbine minus work done by the compressor. So in the open system explanation, we have always said that the work done by the turbine, okay, turbine is always work producing and compressor is always work consuming. Okay, that means to run a cycle 3 to 4 is a turbine. That means for the process 3 to 4 you are going to get some work. That work is work done by turbine. And from 1 to 2 there is going to be a compressor, and that compressor is taking some of the work. So the difference between these two is going to give you the W net. Okay, now again in the same chapter, that means in the open system explanation, we have said that work done by turbine is always going to be the enthalpy difference. in case of compressor also. But in case of turbine, we are always going to take the difference between initial enthalpy minus final enthalpy, because in turbine always compressed air gets into the turbine. Okay, compressed air gets into the turbine, and the air which leaves is the expanded form, and when the air expands, the enthalpy of this decreases. Okay, so we take initial enthalpy minus final enthalpy in turbine. Okay, initial enthalpy minus final enthalpy in turbine. Okay, this is coming this way. Okay, now in case of compressor also, H2 minus H1. Compressor is what? First of all, air gets into the expanded air gets into the compressor, and after that inside the compressor it gets compressed. So after compressing, the enthalpy of that air increases. So in case of compressor, we take final minus initial. Okay, so for compressor, final minus initial. For turbine, initial minus final. Okay, now if you remember, we have always said that enthalpy is nothing but Cp into that temperature. Enthalpy at some point is going to be Cp into that temperature. Okay, so by putting Cp into those temperatures in all these things, we are going to get this expression. So after that, if you take Cp common, Cp, then this is the thing you are going to get inside the bracket, T3 minus T4 minus T2 plus T1. Okay, now from this cycle, T3 is what? T3 is the maximum temperature. T3 is the maximum temperature. Okay, minus T4. Okay, so from here, this is for process 3 to 4. 3 to 4 is adiabatic. Okay, in TS diagram it is going to be isentropic. Okay, so for adiabatic, T3 by T4 is equal to P3 by P4 to the power gamma minus 1 by gamma. Okay, so from this P3 by P4 is the pressure ratio. Okay, so from this equation, if you want to find out T4, it is going to be T3 by Rp to the power gamma minus 1 by gamma. Okay, so we are replacing T4 by T3 by gamma minus 1 by gamma. Rp to the power gamma minus 1 by gamma minus T2 is what again? We are constantly finding out again. If you consider process 1 to 2, okay, in the last board also we have found out that T2 is what? T2 is nothing but T1 into Rp to the power gamma minus 1 by gamma. Okay, so we are finding out that in place of T2, T1 into Rp to the power gamma minus 1 by gamma, and T1 is what? T1 is the minimum temperature here. Okay, so we are writing in place of T1, we are writing T min. So again, in place of T1, I am going to write T min. Here T3 is there, so in place of T3, I am going to write T max. Okay, now for a system to work, the limits of the temperatures are always given. The highest I can go up to this temperature, and lowest I can come up to this temperature. Okay, so in this whole equation, this is the expression of W net. Okay, this is the expression of W net. From that, Cp is going to be constant, T max is going to be constant, T max constant, T min is constant, T min is constant. Okay, and gamma is also going to be constant. That means for a given system and work fluid, we already know the Cp, the T max, T min, gamma. Okay, all these things we know. The only thing that is unknown is Rp. That means what? W net is a function of Rp. W net is a function of Rp. That means W net is a function of pressure ratio. Okay, so since it is a function of pressure ratio, we are going to differentiate the W net with respect to pressure ratio, and we equate this to 0. This is the maximum condition. For maximum condition, we always differentiate this with respect to something, and we equate this to 0. Okay, because if something is maximum, then its differentiation is always 0. Okay, so for this to be maximum, we are going to equate this. That means in the next board, what we are going to do, we are going to differentiate this expression with respect to Rp, and after that, what are the conditions we are going to get by equating this to 0 is going to be our optimum condition. Okay, so in the next board, we are going to differentiate this. Okay, so this is the expression we are going to differentiate now with respect to Rp. Okay, so in this expression, Cp is going to be constant, so Cp will come out of the derivation. Okay, now in the remaining portion, T max and T min are going to be constant. If T max and T min are going to be constant, that means they are going to have 0. The differentiation is going to be 0. Okay, the remaining parts is these two. Okay, so from here T max is constant, so T max will come out. Okay, now we have to differentiate this. Okay, now this is what differentiation is. What this can be written as Rp to the power minus of this. Okay, since it is in denominator, if you want to get it to the numerator, you can put a minus sign before this power. Okay, so we are taking this thing outside. Okay, this is the formula for x to the power n. If there is x to the power n, differentiation of x to the power n with respect to x, you need to take down n. Okay, n into x to the power n minus 1. So I am taking down this n. Since there was a minus here, we are converting this minus into plus. Okay, so this thing is coming here, and the remaining thing, that means the rp to the power minus of this minus 1 is this one. Okay, in the next one, t min is going to be constant again, and this thing will come up here, come down here, and rp to the power this minus 1 is going to give a result like this one. Okay, so after this, you want to take common. Okay, you can take common gamma minus 1 by gamma and gamma minus 1 by gamma from there. Okay, so after taking common cp into this, and the remaining thing is this one. Okay, and the remaining thing is this one. So after that, if you see, this thing is completely constant. Gamma is going to be constant, cp is going to be constant. So this term cannot be 0. But if the product of this and this is equal to 0, and this thing cannot be 0, that means this part is going to be 0. Okay, that means this minus this is going to be equal to 0. Okay, now if you see, this minus this is going to be 0, so we can remove the 0 and we can put an equal sign here. Okay, if the difference between two things is going to be 0, that means these two things are equal, so this is going to be equal. After that, what we are doing, t min by t max we are taking in one side, and rp to the power this by rp to the power this we are taking on other side. Okay, so the final result is rp to the power this, okay, minus of this one. So minus of 1 by gamma becomes plus of 1 by gamma. Okay, now if you calculate this, okay, you are going to get this thing. Okay, if you simplify this, you are going to get this thing. Okay, so in the next thing, what we have done, this was t min by t max. Now we have done t max by t min, because there was a, if you do this, there will be a minus sign here. Okay, to remove this minus sign, we are taking the reciprocal of t min by t max, that is t max by t min. Okay, so this is the optimum condition for your maximum W net. Okay, so in some questions, if this is given like this in a Breton cycle, to take the maximum net work, what is going to be what should be the efficiency? Okay, now efficiency formula is what? Efficiency is 1 minus 1 by rp to the power gamma minus 1 by gamma. Okay, now they have given to get the maximum work output, what is going to be the efficiency? Okay, now this is our condition to find the maximum net work. Okay, that means if your net work to be maximum, okay, to your net work to be maximum, this is the condition. Your pressure ratio must be this. Okay, your pressure ratio must be this. So if they ask for getting maximum W net, what is going to be the efficiency? Nothing to worry, you are just going to put the value of rp. Okay, you are just going to put the value of rp for maximum W net here. So after that, whatever the efficiency you are going to get is going to be your efficiency for maximum work output. Okay, so this is the condition for our optimum condition for our, you can write it as rp optimum. Okay, that means this is the optimum condition for getting the maximum net work output. Okay.